Hello and welcome back. This is video 3 of 3 for Chapter 12. And Chapter 12 introduces us to sources of magnetism. Um, in the last two videos, we talked about how current produces magnetic fields, specifically magnetic fields that have a tendency to loop. And as I mentioned, that is one of the properties of a magnetic field is that it loops back onto itself. Um, what I'd like to do today is to talk about sources of the magnetic field that aren't explicitly a consequence of flowing charge. Now, obviously, uh, you have seen a permanent magnet before. For example, if you stick something to your fridge with a magnet, that's a permanent magnet. And you'll notice that if you actually grasp the magnet, you're not shocked or anything like that. So clearly, if there is current flowing causing the magnetic field that's there, it's not directly accessible to you, and it can't hurt you. So what's really going on here? Well, um, the first thing I'd like to point out is that the visualization that we're going to use to create the magnetic field is actually wrong. We have a tendency to want to relate things in terms that we understand. For example, when we think of the motions of the electrons around the nucleus of an atom, we think of planets orbiting the sun. Um, that's actually not true. That's a gross simplification of the situation. And when you get down to the quantum mechanical realm, things don't behave like you expect. They don't behave what we say macroscopically. It's just not what they do. They behave microscopically. So, if you think about an atom using this very wrong but unfortunately necessary visualization, you have a nucleus, we'll say right here, and we'll consider the simplest atom, hydrogen. And right here, we'll say is the path that an electron takes, going around the nucleus like this. Okay. And in fact, why don't we just sort of separate the nucleus out from everything else to make it clear? We'll give it a color, just like that. And here's our little electron. Here's a proton sitting at the center. Now, um, electrons we know have a charge. So let's pretend that this electron orbits like this, goes around like that. Well, what you have here is charge that is moving in a circle. If you remember the previous video that we did, one of the solutions we did was current flowing in a hoop or in a circle. And we looked at the magnetic field that sits above that particular hoop at the center. And what you end up with is, as a consequence of this moving electron this way, we'll say, is current that flows this way. Now, why is it in the opposite direction? Well, go back and review the section that we talked about some time ago with respect to the conventional direction of current flow and what's really flowing. So here, if you were to take and sort of wrap your fingers around in the direction of I, you would have a thumb that would point at the very center into the page, and that would be the direction of this induced magnetic field. So this is from orbits. Okay. Now, the electron itself, if you think again of it sort of like a planet orbiting the sun, you can very grossly and wrongly say that it spins on its axis. So, here's your little electron, like this. Maybe it rotates around like this, in this direction. It has a negative charge, and as a consequence, you could think of that as charge rotating this way. That's positive. That would be the direction of I. And again, if you wrap your fingers around in that direction and look at your thumb, you end up with a magnetic field that would point down like this. Okay. So you can think of these orbits of charges as sort of like little bar magnets. So there's magnetism there. And then the electrons themselves spin, and as a consequence, they're magnetic as well. And how the electrons sort of add up inside an atom gives you different types of magnetism. So that said, there are three basic types of magnetism. You have paramagnetism, you have diamagnetism, and you have ferromagnetism. Now the difference between them is how strongly they react to the presence of an external magnetic field, and also exactly what their reaction is. For example, and we're going to go into these in much greater detail in a moment, paramagnetism, when you take a paramagnetic material, examples of which would be something like uranium, aluminum, what have you, even oxygen. Okay. When you take and you place a paramagnetic material in the presence of a magnetic field, some of the atoms, again, which are naturally magnetic, will align up with the magnetic field. Many of them will not. We're going to talk about why that is when we go into more depth about paramagnetism. But as a consequence, you have a very weakly responding material. So it responds weakly, to a magnetic field. So it's weakly attracted. Now we'll talk about what that means here in a moment. On the other hand, diamagnetic materials, for example, helium is one, have no real intrinsic magnetism. That is, when you look at how the electrons in their orbits and in their alignment line up, basically for every one electron that gives you a magnetic field that points this way, there's going to be another one that sort of points this way, and they're going to cancel out to give you no net B, even though individually they may be magnetic. And you'll see what happens here, because what happens is when you place a diamagnetic material in the presence of a magnetic field, what happens is the orbits of the electrons and what have you line up to actually go against it. And that's true for paramagnetic materials and ferromagnetic materials. They have an intrinsic magnetism to them, and then there is this weak opposition as a consequence of what you could think of as almost like a magnetic dipole. And in truth, that's really what it is. And so the dipoles line up against, and so these things actually are weakly repelled. On the other hand, ferromagnetism represents the strongest magnetism of all. It's far, 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 far stronger than paramagnetism. A good example of which would be iron, hence its name. Other materials that are ferromagnetic, nickel is a good one. I believe maybe cesium is too. I'd have to check that out. For some reason, I'm recalling that it's ferromagnetic as well. And these things are they very strongly respond to magnetism. Let me double check that cesium so I'll make sure I'm not lying to you. No, actually it's paramagnetic, so I did lie to you there. Okay, so that said, let's talk about these in specifics. So we'll start with paramagnetism. And so if you go back to sort of our model of an electron orbiting the nucleus of an atom, and let's think of this as sort of being on edge of the orbit there, and there's our nucleus right there in the center. And here's our little electron going around like this. So what you have is you have current. You have current going around in a circle like that. And we know that this represents a magnetic moment. Okay. So in this situation, let's see, in this case, I'll tell you what, this is actually drawn a little bit incorrectly. So what I'm going to do is have the electron go around this way just to make my life easy. So what that does is to reverse the direction of the current flow. So here, if you were to put your fingers in the direction of I and sort of loop them around, your thumb is going to give you an idea of the direction of P or mu. So here is your magnetic moment right there. Okay. Now, just as an example, if you were to look up oxygen and look at the contribution of all the electrons that are orbiting, all the spins of the electrons on their axes, even the contributions of the nuclei, where there's some weak magnetism going on there, what you would discover is that you would end up with a magnetic moment that was somewhere around 13.9 times 10 to the minus 24th ampere meters squared. Okay. So if you were to go back and review the energy of a magnetic dipole like this that's caught inside a magnetic field, and look at the difference in energy of them being lined up with or lined up against the magnetic field. What that does is that gives you a total possible like a maximum of the potential energy that you would have trapped inside. So the energy of a magnetic moment or a magnetic dipole looks like this. So it's the dot product. We derived this I think back in chapter 10, I believe. So anyway, lining up against would be, we'll say, mu going this way and B going this way. And when you do your dot product here, you would get a -1. A minus times a minus is a positive. So against would be just mu times B in magnitude. With would have mu pointing this way and B pointing this way. And again, you do the dot product, you get 1 in this case instead of -1. And with would be minus mu times B. So your total possible change in energy here would be this minus this, which would be 2 mu times B. So this would be the total possible difference in potential energy that you would see in here. Any other alignment is going to give you less potential energy. So let's just think about a simple example. We're going to put this particular material in the presence of a very strong magnetic field. I don't know, maybe B is something like 1.0 Tesla. Tesla's a lot of magnetic field. So in this case, the difference in potential energy you would see here would be 2 times mu, which is 13.9 times 10 to the minus 24th ampere meters squared times 1.0 Tesla. So you do this, this is just multiplying it by 1. 13.9 times 2 is, 27.8. So this would be something like 27.8 times 10 to the minus 24th joules. Or if you wanted to be, technical about representing this properly in scientific notation, that many joules. Okay. Now, so again, this would be oxygen in the presence of a magnetic field of 1.0 Tesla. And this is just one oxygen atom. All right. But now I want you just to consider any ambient energy that we have sitting around, specifically energy that has a tendency to randomize orientation. For example, thermal energy. We know that, in the subatomic realm, things are random. So, we also know that, the potential energy as per temperature would look something like for just a plain old monatomic gas, 3 halves K sub B times T. So imagine a gas kept at standard temperature and pressure, thus experiencing, this magnetic field being passed through it. Well, the energy that you would have as a consequence of this temperature being, that sort of is present in your material, causing randomization, if you will. This is 1.38 times 10 to the minus 23rd joules per Kelvin. And at standard temperature and pressure, that's 273 Kelvin. Well, if we do the math here, you end up with something like 5.65 times 10 to the minus 21st joules. Now this is randomization energy is the way to think about this. So as a consequence of the random motions of the atoms and molecules inside the gas, as they collide, what that's going to do is constantly mess around with their orientation, including the orientation of their net magnetic moment. So if you were to look at this energy and compare this to the energy that at a maximum sits between the orientations right here, you'll see that this is, basically about 2 orders of magnitude greater. So it's about a factor of 100 times greater than this. So as a consequence, and this is true for all paramagnetic materials, as a consequence, just the presence of thermal energy is enough to cause sort of the randomization that occurs, that as a consequence misaligns the vast majority of the atoms inside this material with the magnetic field. So very few atoms align. And as a consequence, it's weakly magnetic. Now, the next one I want to talk about would be diamagnetic materials. And we've actually pretty much talked about those to the degree that it really matters, because here, the reason why these things are diamagnetic is because if you look again at the orientation of the electrons that are doing their orbiting and spinning, they sort of balance each other out to give a net magnetic moment of 0. So any magnetic moment that's going to be present is going to be a consequence of you passing the field through. So when you pass the magnetic field through, what that does is to create natural opposition to the field that you pass through. And as a consequence, you have repulsion. Attraction occurs when things line up. Repulsion occurs when when things are opposite like this. So there's a natural magnetic field that occurs that opposes the one that that you're passing through. And so you have weak repulsion. Now lastly, but definitely not least, is ferromagnetic materials. Now, the key points here are that the atoms are very magnetic. So, for example, in iron, the majority of the electrons line up to give an iron atom a very, very strong magnetic field. Not only that, um, if you think of a piece of iron that's been cast, the atoms themselves sort of group up into what we call domains. So you have this region like this of atoms who are sort of bound together via interaction, and their magnetic fields all point roughly in the same direction. So what happens is if you were to, for example, pass a magnetic field through this, these things are going to want to tilt and line up naturally with it, and they do it en masse. They do it in groups. Okay. And because this is a group action, when you turn your magnetic field off, they have a tendency to maintain this direction. Now, the the act of maintaining the direction of the magnetic field that was originally passed through and holding on to that direction when you turn it off is called hysteresis. And this is the reason why you can turn a bar of iron into a permanent magnet. So, imagine for a moment that you had molten iron that you poured into a mold and then you passed a magnetic field through it. Well, the atoms are very magnetic, they line up with it. And then as it cools, they maintain that orientation, which means the domains, are going to net pass, or they're going to net point in that direction. So when it's finally cooled down, what you've done is you've created something that's magnetic. Okay. You could even take an iron clothes hanger, locate north and south using a compass, line up your clothes hanger with north and south, and then beat it with a hammer. And what would happen is each time you impacted it with a hammer, it would bounce the atoms that are pointing not against or not with the magnetic field around, and they'd naturally want to start to point. So you can literally make a magnet that way. And in fact, most buildings, if they have metal door frames, the metal door frames are magnetic, and that's a consequence of people opening and shutting the doors. And the Earth's magnetic field causing gradual alignment over time. So the trick here is with ferromagnetic materials, you have domains that are very organized, and when you pass an external magnetic field through it, they have a tendency to want to hold on to that direction through hysteresis. Now, that said, let's talk about what happens just sort of in general when you pass a magnetic field through a material. So I want you to imagine this as sort of being a block of, we'll use iron as a good example here. And maybe here's your magnetic field that you pass through. Okay. Now we're going to separate this up into groups. We have the external magnetic field. We're just going to call this B, and it's going to be a combination of the original field plus any induced or present field. Now we're going to have the original one. That's the one that you pass through. Its field strength would be whatever it is if the iron wasn't there. So we're going to call that B naught. Now, one way you can visualize the the domains and the hysteresis is going to occur due to this is by thinking of there being current present. Now, it's a bit of a misnomer, but it's a way of modeling the hysteresis uh, by sort of pretending that there has been an induced current. Okay, and your book says surface. It really is over volume. So the induced B, and this is only the induced stuff, we're going to call B magnetic. So your external field B is going to be a combination of what you pass through plus the quote unquote induced current. That really is just a consequence of these things lining up through their domains to give you your additional magnetism, if you will. Now, thankfully, though, this alignment is going to be a function of this right here, which means that B magnetic you can think of as being proportional to how much field that you pass through. Now, the constant of proportionality that we put there is something called chi magnetic. It's the magnetic susceptibility. And that's the relationship between the two. So the field that you would measure, which would be a combination of the field that you pass through and the magnetic effect of aligning the atoms, is going to look like this. And you can just pull the B naught out. Like that. You'll notice that this looks one for one like this. And that was the electric susceptibility for polarization. This is the same idea, okay? So back then, basically what you would say is you would say that your electric field is equal to something kappa electric, will say, times the original electric field. So what you would do is you would call this right here um, chi magnetic. And chi magnetic is something you really would call the relative permeability. And it occupies the same position in magnetism as epsilon and epsilon naught's relationship to each other do. So back in electricity, you would say that your your permittivity is equal to kappa sub E times the permittivity of free space. And here you would say your permeability is equal to kappa sub M times the permeability of free space. So this is where you actually fit in the effects of a material. For example, if you were to place it within the center of the solenoid, kind of like you can place a dielectric, between the plates of a capacitor. And what that does is to enhance your capacitance. You can place, a slab of metal inside a solenoid, and you can affect its behavior as well. And just as an example, let's take a look at this problem right here. So we have a solenoid here that's 10 centimeters long and has 200 turns to it. If half an amp of current is passed through it, What I'd like to know is what's the resulting magnetic field, and what is the magnetic field? And that should be if a core of aluminum is placed inside. Now, we're also going to look at a slab of 99.9% pure iron. There's a reason for that. I'm going to talk about that in a moment. So, so this is actually a pretty easy problem. We've been given, the L, the length, is 10 centimeters or, 0.10 meters. We're given the amount of current I, which is 5.0 amps. And we also know capital N, which is the number of turns, and that's 200. So if you remember, the magnetic field in magnitude due to a solenoid, we derived, I believe it was last lecture. It looks something like mu naught times N times I. And lowercase n was the number of turns per unit length. Okay, so here this would just be mu naught capital N I over L. So mu naught is 4 pi times 10 to the minus 7th Tesla meters per ampere. We have 200 turns. The current is 5.0 amps. And the length is 0.10 meters. So you do the math here, and you get times 10 to the 7th times 200 times 5 divided by 0.1. Okay, so you get something like 0.0126 Tesla, about that. So here's the answer to part A right here. Now what about part B? Well, the way you get from A to B is through either the susceptibility or the relative permeabilities of aluminum and of iron. Now I'm gonna use susceptibility just because that's the word of the day with respect to magnetism right now. And the susceptibility of aluminum from a magnetic standpoint is 1.2. Now for iron, actually let me just write it as Fe to be consistent here. For iron, it varies. The susceptibility isn't linear. It's not just a constant like this. It goes anywhere from about 149 to 4,999. So it varies tremendously. So what we'll do with the iron one is we'll look at the upper and the lower bounds. And so remember, the relationship between the fields is that B is equal to 1 plus chi times the original field. This is just from a magnitude standpoint. So for aluminum, the act of placing a core of aluminum in the solenoid is basically like you taking and multiplying the amount of field that's present by a factor of 2.2. Oops. All right, so if I multiply this by 2.2, I get 0.0276 Tesla. So this is for aluminum. Now remember, aluminum is diamagnetic. Now for iron, though, as you can see, it's going to be substantially different. So the lower limit would be 1 plus 149. So that's 150. And what that does is to bump our magnetic field strength up to about 1.88 Tesla. That's the lower limit with this one. The upper limit is going to be 1 plus 4,999 times that. So, let's see. That's 5,000. And that's about 62.8 Tesla. So as you can see, placing this core in here, what it does is to tremendously increase the magnetic field. Okay. So the original magnetic field, due to the current flowing through, is what causes this. So what that does is to cause alignment. Here in aluminum, it's weak alignment. You know, causing a small enhancement of your net magnetic field, but not a whole lot. In iron, though, iron is no joke, because here you're enhancing the field by anywhere from 150 times to, 5,000 times. So, this is a substantially strong effect, and it's something that we'll be talking about more later on as we get close to the end of the semester. All right, so that's it for this video, and I'll see you in the next one.